Hello, and welcome to our talk on our paper submitted to the IFAC World Congress 2020. I'm Michelle Chong, and this was work that was done in collaboration with Henrik Sandberg. Here's an outline of the talk. I'll start off by giving a brief description of what an inverter-based power distribution network is, so that we're all on the same page. This will be followed by formulating the voltage regulation problem. I'll then highlight what is new in this work, and then introduce the mathematical model that we've chosen, and present the class of local controllers that we've designed to achieve a voltage regulation objective. Our result is illustrated on a benchmark model, and I'll conclude with a summary. This is how an electricity network is generally structured. At the transmission level, we have energy sources such as nuclear, water, and coal, which forms the high voltage transmission network. This is then stepped down to a low voltage and distributed to customers such as ourselves via a substation. The level that we're concerned with is a distribution network, highlighted in red. Traditionally, customers who are connected to a distribution network are only consumers of power. In this day and age, where more and more customers have their own devices to harness renewable energy, such as wind and solar, the customers can also become producers of power. This has the potential of causing voltage disruption up and down the distribution line, and therefore there's a need for control mechanisms to regulate the injection of power into the network, which then influences the voltages received by each customer. This can be achieved via DC to AC inverters, which usually comes equipped with each renewable energy device. These function as our actuators, and our aim is to design controllers which regulate the voltages received by each customer. The setup is as follows. The substation transmits the set point voltage to each customer, and the objective of all the controllers sigma i's is to ensure that the local voltages Vi remain within a desired safety margin, which is formally written as follows. Before we dive into our contributions, I'd like to point out a drawback of our previous works in solving this problem, presented in these references. The plot we see here shows the power output of each solar panel on a typical sunny day in Vienna. We see that before dawn, there is not much output, and the output increases as the sun rises, and peaking around 3 p.m. in the afternoon, and declining as the sun sets. In our previous design, we used the upper bound of the net power consumption over all time, which is the value that we get at around 3 p.m. This leads to a very conservative controller design. The aim of this paper is to address this issue, and this is achieved by considering predefined observation windows. For example, from 5 a.m. to 8:30 a.m. to 11, and so on. The aim is to provide a redesign of the controller at the start of each observation window based on the upper bounds of the data in that time window, which is known beforehand. And this could lead to less conservative designs. Before delving into our controller design, let me present the model that we have used. Recall that we considered a distribution network in a lined configuration, where we have the substation at the head of the line, and the customers connected to the network in a radial fashion, as seen here. In this cartoon, I've tilted our previous cartoon by 90 degrees to match the schematic on the right, which provides a visual on how we model the network. Each customer is modeled as a DC voltage source connected to the inverter, or also known as the controller, which connects to the substation at the head of the line via the network. The distances between the nodes here are captured by the impedances Z and Z primes. The active power is denoted by capital and small p's, and the big and small q's are the reactive power. The voltages at the point of connection to the distribution network are denoted by the V primes, and the voltage received by each customer are denoted by the V's without the primes. Each controller receives the set point voltage, V bar, from the substation and can measure the local voltage, VIs. Now, assuming that the power losses in the distribution line are negligible, we use the model by Baron and Wu from '89, which describes the power flow in the line, as seen in the first two equations here. The next two equations describe the point-to-point voltage in relation to the power flow between these points. The response of the inverter is modeled as follows, where tau I is the time constant of the inverter's response. Our objective is to design the function k to achieve the safe voltage regulation objective. Previously, this design was one-off, based on the upper bound on the data over all time. In this paper, we present an adaptive procedure where the function k is redesigned at each discrete time instant, which was predefined, based on the data over the time window, and we prove that the safe voltage regulation objective can also be achieved. Let's dive deeper into the design of the local controllers. Recall from the previous slide that the controller takes this particular form, where k is the function to be designed at the start of the observation window, tk to tk plus 1. Also, we set the initial condition of the controller to 0 at the start of each time window. Now, this choice is completely arbitrary to simplify the analysis and design, but it would also work with other initial conditions. We assume that the function k satisfies two properties. The first property, here, is known as a sector bound in 0 to d. And this means that the function has to lie within the cone sandwiched between these lines in quadrant 1 and quadrant 3. The second property requires the function to be saturated. Pictorially, the intersection of these two properties means that the function has to lie within the shaded region. An example of a function will be the standard droop function used in the voltage regulation literature, which is also known as the droop controller. Our design question would be, how do we choose d and k, d being the slope of this line, and k being the saturation level, such that all the received voltages fall within the desired band? At this point, I'd like to point out our main contributions. First, to the best of our knowledge, we provide mathematical proofs that the safety objective can be achieved with droop control. Moreover, it actually is a whole class of functions k which will meet the safety objective in this context, and this extends beyond the standard droop function considered in the literature. For example, a smooth function also belongs to this class of function. One feature in which our droop controllers is different from the ones in the literature is that the input to the function k is the difference of squares instead of just the error. This is the result of how we've chosen to model the distribution network. And finally, the main focus of this paper is that each controller is redesigned at the start of each observation window, based on the upper bounds of the data in that time window, which is known beforehand. Moreover, we only need to know this upper bound rather than the actual values of the net power consumption, which preserves the privacy of each customer. Putting all these together, and for the purposes of developing our main result, we restate the safety objective in different coordinates as follows. In terms of yi, which is the difference between the square of the set point voltage and the local voltage received by each customer. Here, the safety objective is highlighted in purple and implies the original objective in green by setting epsilon as written. For the purposes of analysis, we can write the model compactly as shown, where we have a Lura system with a linear part here and a nonlinear part with the function k, where k is redesigned at the start of the time window tk to tk plus 1. the initial condition of Q of the inverter is set to 0. The output of our system is Y, which is our objective signal. And our objective is to regulate this signal such that it is within a specified margin. We assume that the sequence of the update time instance are known. In other words, the observation time window has been predefined. And we also assume that the upper bound of the data are known. Our main result is, given the desired margin epsilon, if there exists a delta phi, which is a function of the known upper bounds on the data, the deltas, and if there exists an epsilon y such that it satisfies this inequality, then there exist design parameters d and k bar, and maximum and minimum time constants of all the inverters satisfying condition 10 in a paper, such that the new safety objective, highlighted in purple, is achieved. The details of condition 10 is written in our paper, which I've not reproduced here. To prove this result, we have used a trajectory-based proof, which I will sketch as follows. Firstly, we note that the individual yi is upper bounded by the max of all the yi's for all time. And from our compact model written on the left, the norm of y is upper bounded as written. In the following steps, I'll sketch how each of these terms can be bounded. For the bound on the first term, we can obtain it from the properties of the function k, namely its sector boundedness and it being a saturation function. And this is achieved via the design parameters d and k. For the bound on the second term, we can obtain from the bounds on the data, which is known a priori. Further, this term also depends on the number of customers connected to the distribution line, which is finite. Now for the third term, we recall that y0 is the difference in the square values of the set point voltage and the voltage at the head of the line. This variable is assumed to be upper bounded by epsilon y. Putting all these together, the new safety objective is met by choosing the parameters d and k according to condition 10 in the paper. We now move on to see how this performs on the benchmark model. Here we have considered the residential feeder of an European grid with 5 customers. At the head of the line, we have the substation denoted by S1. Each black arrow denotes a measurable point in the network. The green arrows denote a load, which are the customers of this distribution line. In this network, there are 5 customers at R11, R15, R16, 17, and 18. Each section of the line has been depicted by a white rectangle to denote the line impedance. It is not difficult to see that this benchmark model can be captured by our general line model on the right. This means that we can go ahead and apply our adaptive controller design to this benchmark model. Here I've shown the active and reactive powers consumed and generated by each customer, where each of the colored lines is the data of each customer. Over the course of the simulation, we considered 3 time windows of length 100 seconds. At the time points 0, 100, and 200 seconds. We redesigned the function k according to our method, which provides us with the d and k design parameters, which describe the slope and the saturation level, that guide the choice of the function k. For the purposes of this study, we use the conventional droop function as shown, where the slope d and k are determined by our condition. The 2 plots that we now see show the injected reactive power generated by the controller. And as guaranteed by our adaptive design, we see that all the voltages lie within the specified margin indicated by the dashed blue lines. What we've seen so far confirms the main result of this paper, Now, how does this compare to the case where we do not adapt the design according to the data in the predefined time epochs? In a non-adaptive case, we see that while the voltages still remain within the desired margin, as guaranteed by our previous work, the required effort by the controller is much larger than the adaptive redesign presented in this paper. To summarize, we have provided a guarantee for voltage regulation in a power distribution network in a line configuration. Our proposed method allows the operator to specify the margin of error, and the local controllers are then designed to meet this criteria. We showed that a whole class of functions can achieve this task, which extends beyond the standard droop law used in the literature. One difference between our results and the other results in the literature is that our proposed droop function takes as an input the difference in the squared voltages, as opposed to just the difference. This is a consequence of our modeling choice. And finally, the main crux of the paper is the adaptive redesign of the droop function at the start of the predefined time windows based on known bounds on the load consumption, which are known beforehand. And as we can see in our simulation study of a benchmark model, this leads to a less conservative design. With this, I'd like to conclude my talk, and we thank you very much for your attention.